we concluded the lecture by presenting the problem, so that when you write the martingale, you have an expression which is not a function of the empirical measure, and in a certain sense you have to close the equation. So to close the equation, I will present to you what's called the entropy method. But for that, I will need many tools. So today, I will present the tools which are used in this entropy method. So we go back to Markov chain. So E, it's a finite state space. Xt, it's a continuous time Markov chain taking values on E. And we have a generator. So this Markov chain has a generator which is represented by L, so that L of F, let's say that we will represent the points by X, it's given by the sum over all Y in E of R X Y Fy minus Fx. And I'm always assuming that this chain it's irreducible, so let's represent by pi the unique stationary state. So this is the context, and in this context I want to introduce the entropy and what's called also the Dirichlet form. So the entropy will be in some sort of distance between probability measures. So I want to define the relative entropy of a probability measure mu with respect to the stationary state pi. So mu and pi are probability measures in E. And the entropy will be defined by a variational formula. So this is the supremum over all functions which are continuous and bounded on E. But since E here, it's a finite state space, all functions are continuous and bounded. So here it's a supremum over all functions of the integral of f d mu minus the log of the integral of the expectation of the exponential of f d pi. Okay, so this is the definition of the relative entropy of mu with respect to nu. And why it will be used? Well, this is a supremum, which means that f d mu, it's always bounded by the entropy of mu with respect to pi plus the log of the integral of exponential f d pi. So this means that for all functions which are continuous and bounded, I can estimate the integral of f with respect to mu by the entropy of mu with respect to pi plus the log of the integral of the exponential d pi. So this is how we are going to use the entropy. And let me observe that, well, this is true for any functions f. So it's true for the function f if I multiply f by gamma. So let's multiply f by gamma. So this is true for all f and all gamma. So f now it's fixed. So this is true for all gamma. And now let's assume that gamma is positive, and let's divide that by this inequality by gamma. And what I get is the following inequality. Okay, that this is true for any gamma. So again, I have a bounded continuous function. I want to estimate this integral, and I have this bound. Okay, which means that if I am able to estimate the entropy of mu with respect to pi, and if I'm able to estimate this type of integral, then I'm in business. Okay, I know how to estimate this integral. And what will be the context? The context will be in Markov chain. You start with a measure mu. So this is the initial state. This one, it's known. You know you're starting from a certain initial state, which you know. And then you have a stationary state pi, which is also known. Okay? We have seen in our examples that if you take the Bernoulli product measures, you have a stationary state. So pi, which is the stationary state, and mu, which is the initial state, are known. So I can compute the relative entropy of mu with respect to pi, for instance. Okay? Now I let the process evolve. So I started with pi, and at a certain time I have a new distribution, which is mu pi t, which I will represent by mu t. And this distribution, I have no idea what it is. Okay? I just know it's a distribution. And usually, you face the problem that you want, so you started from mu, you let the process evolve up to time t, and you want to estimate the expectation of a certain function, f. Okay? So this is just the integral of mu with respect to mu pi t. Okay? So it happens that you want to estimate such quantities. Now I can use the entropy inequality in order to use that. I just look at the entropy inequality, and this tells me that this is bounded by 1 over gamma, the entropy of mu pt with respect to pi, plus 1 over gamma log the expectation of the exponential of gamma f with respect to pi. Okay? Pi, it's known. So I can compute this integral and I can estimate it. The problem is this entropy. This entropy, well, this measure I don't know. So I don't know how to estimate this entropy. Well, but it turns out that for a Markov chain, the entropy decreases in time. If I'm taking the relative entropy with respect to the stationary state, we will prove that it decreases in time. So this means that this is bounded by the initial entropy, and therefore I can estimate both terms in this inequality. Okay, so I estimate these two terms, and then I optimize over gamma to get the best possible estimate. Right? So the point is, first, that we have to show that indeed the entropy decreases. Okay. And then, well, you'll tell me, okay, how do I estimate this entropy, which is given by this variational formula? It looks awful to estimate this entropy. Well, actually, we have an exact form of the entropy. The entropy of mu with respect to pi, it's equal to, well, the integral of d mu d pi log. So this is the Radon-Nikodym derivative of a measure with respect to another, d mu d pi. If mu, it's absolutely continuous with respect to pi. Otherwise, it's plus infinity. So you have an exact formula, a simple formula for the entropy. So this term will be easy to estimate, and this one, well, it's an integral with respect to a stationary state. Okay, so we have two questions, two problems to prove that this explicit formula for the relative entropy, and then to prove that the relative entropy decrease in time provided pi is a stationary state. Okay? So this is what we will prove, these two statements, and these sequence of inequalities show how we are going to use this inequality. Fine? So let's start by proving, so let me call that a lemma. Let's prove this identity. So if mu is not absolutely continuous with respect to pi, so here I'm forgetting that pi is a stationary state. Okay? I'm taking two measures, and I'm just defining the relative entropy by this formula. Okay? Because we know that if pi is the stationary state, it puts a positive mass over all points, and therefore any measure it's absolutely continuous with respect to pi. Okay? So let's forget, let's assume that pi, we don't have a Markov chain, we have just two, we have a reference measure pi, and we are computing relative entropy with respect to this reference measure. Okay? So now let's assume that pi, it's not absolutely continuous with respect to pi. I want to prove that the entropy it's equal to plus infinity, which means that I need to find a sequence of continuous functions for which this supremum is equal to plus infinity. Okay, and the idea it's very simple. If mu it's not absolutely continuous with respect to pi, this means that there exists a point x in E such that pi of x it's equal to 0 and mu of x it's really positive. Right? We are in a finite space, so everything is very easy. So what I will do, I'll take the function f. So let me call this point, okay, x. So f of y will be equal to a times delta yx, which means that if f of y is 0 everywhere, and but at x, and at x, f of y is equal to a. So I know that the entropy of mu with respect to pi, it's larger than this expression computed at f. And if I go to this expression, you see that f is 0 everywhere. So here I get just a times mu of x. Then minus, here I get, well, f is 0. F is 0 everywhere, but at x. So that will be 1 times pi. So this gives me the sum of y different from x of pi of y. And then at x, well, but at x, pi is equal to 0, so this expression do not appear. Okay? So that will be pi of x of exponential a, right? But pi of x is 0, so this is just the sum over all y of py, but pi, it's a probability measure, and since pi of x is 0, this sum is 1. With the logarithm, it becomes 0, so this is actually equal to a mu x. Okay? Now, you send a to plus infinity to get that the entropy, the relative entropy, is plus infinity. Fine? Okay. So we proved already that it's plus infinity if it's not absolutely continuous. So let's assume now that mu let's assume that mu is absolutely continuous with respect to pi. And let's say that the support of pi is equal of E. Okay? If the support is a subset, this means that all these sums are actually restricted to this finite subset. Okay? So what I have, it's a supremum over f of the sum for x in E of fx nu x minus the log of the sum over x of the exponential fx by x. All right, so this is a function of E variables. Okay, this is a function phi of fx1, fx, let me call it n, if n is the total number of points of E. Okay? So I'm understanding these are real numbers, fx1 up to fxn, and therefore this is a function of all these variables. Okay? And, well, this function phi, you see here, it is linear, while here it's convex, so it's a concave function. So phi, it's a concave function. And therefore, I need to find the critical point of phi. So let me compute the derivative of phi with respect to fxj. Okay? And let's impose that this is equal to 0. So what's to find the critical point? So what's the derivative of phi with respect to xj, fxj? Well, in this first sum, it's mu xj. So this is the first term, it's mu of xj. Then minus, I have a logarithm, so this is 1 over the sum of exponential fy py. And then the derivative of this expression with respect to fxj, so this is exponential fxj by xj. So this is the partial derivative of phi with respect to fxj. And this has to be equal to 0, which means that mu xj so this means that mu xj has to be equal to the exponential of fy py exponential fxj by xj. Okay, and this is for all j. Right? So note that with this definition, mu, it's indeed a probability measure. So this gives me that mu xj has to be equal to that. So that the critical point is given by these fxj, which satisfy this identity for all j. Okay, so what I want to say is that this characterizes the fxj, right? I get that fxj exponential should be equal to a constant times mu xj divided by pi xj, from which I get that the log, or taking log on both sides, that f xj should be equal to a constant plus the logarithm of mu xj and pi xj. Okay, so up to a constant, fxj has to be given by these an additive constant. And what you observe, that if I, in this equation, add a constant, it doesn't change. So in this phi, if I add a constant to each c, in the first term, what I get, it's c, because mu, it's a probability measure. And in the second term, I get an exponential c, which multiplies. So I get a log of exponential c, which is c, which cancel. This means that this function, it's constant by in this direction. So if I add to every point a constant c, every coordinate a constant c, this function is constant. Okay, so it's constant along this line, and therefore, which means that I can choose here any constant I wish. So let's take it 0, and what we get is that these points are critical points, and in particular, this function phi gets its maximum value at f given by this expression, where I'm free to choose C0, so let's take C0 equal to 0. So the supremum over f of phi of f, well, it's equal to the sum x in E of f, but f, it's the log of mu x divided by pi x minus the log of the sum of exponential f, but exponential f, it's mu x divided by pi x times pi x. Okay, so this is the value of the supremum. And now you see that pi will cancel with pi. The sum over x, it's equal to 1 because mu, it's a probability measure. So here it's 0. And so this is the supremum. And of course, I forgot to write mu x. Sorry for that. So here in the first term, it's f. F, it's log of mu divided by pi. Okay. So f, it's log. But it's integrated with respect to mu x. Sorry about that. So as I said before, this second term is equal to 0, while the first term is what it is, and I can rewrite this second term as to get exactly the same formula as I wrote there, mu x divided by pi x log mu x divided by pi x times pi x. Okay, and this is the formula I wrote over there. Fine, so I defined the entropy by this variational formula, and we just proved that it has an explicit version, which is given by that. Okay? Yeah. The fact that it's absolutely continuous, you mean? No, say it again. What you?
I am asking if you use it to prove the existence of such mu with these values. Because if pi is 0, where mu is not
Yeah, I mean, if mu is not absolutely continuous, what you get is that you are able to construct a function which explodes.
Yeah, but I was asking if the only time you use the fact that mu is absolutely continuous in this proof is this.
Yeah, it's in getting that this has a solution, that this equation has a solution. Okay, if mu is not absolutely continuous, we could not find this function f. That would not be defined. Okay, so first step, we have the entropy given by variational form, and now we have an explicit formula. Questions? Okay. So now, let's turn to my second statement, which is that the entropy decreases in time. So now, it's important, pi, it's the stationary state of a Markov chain whose semigroup is PT. So maybe let me write the lemma here. So the lemma, it's again, so you have a Markov chain, xt. PT is the semigroup. This Markov chain is irreducible. Pi is the stationary state. And what I claim is that mu pi t h, so the relative entropy, that this is differentiable and the derivative it's bounded by 0. Okay? So what I will do is pi is the stationary state, so it gives a positive measure to any point. So every measure is absolutely continuous, and therefore, so what I will do, I'll start the proof, then I stop because I will need an identity, and I will come back to the proof. Okay, so, but I just want to. So I just obtained an explicit formula. Okay? So this is mu pt. Oh, okay. So let me write it in the log d mu pt d pi d pi. So let me call ft. So mu pt, it's absolutely continuous with respect to pi. Let me call ft the Radon-Nikodym derivative. So ft, it's d mu pt d pi. Okay, with this notation, I can simply write this integral as the integral of ft log ft d pi. And my problem is, well, I want to take derivative. It's to compute the derivative of ft with respect to t. Okay, so let me stop here and let me compute this derivative. Okay, so pi is the stationary state. So we introduced the space L2 of pi. We have seen that L is an operator in this space, and we represent it by L star the adjoint. So the adjoint means that LFG, scalar product in L2 of pi, it's equal of F L star G. Okay, and this holds for all f and g in L2 pi. So this is the definition of L star. We are in a finite state space, so it always exists. We don't have to bother with the domains. And my lemma is that if I take the derivative of ft, that this is equal to L star ft. So I have a formula for ft, the derivative of ft. Okay, so proof. So for that, I will consider ft g, and I will take the derivative of this expression. And the idea is after, if I want this derivative, it's just to take g as a function which is equal to 1 at one point and 0 everywhere else. Because then this integral will be ft at that point times pi of that point. Okay? So let's compute this derivative and check what it is. Well, this derivative, it's the sum over e of pi x, which is the measure, then ft of x, gx. Just the scalar product. Now, let's recall what ft of x is. Let's recall what ft of x. Ft of x is the Radon-Nikodym derivative of mu pt with respect to nu. And this is just mu ptx divided by pi x, because we are in a finite state space. So here I forgot, of course, the derivative in time. So let me just replace ft of x by what it is. So this is the time derivative of the sum of pi x mu pt of x divided by pi of x and g of x. That's fine, but this is equal to ddt, the sum over x. Then you see that pi of x cancel with pi of x, and you get mu pt of x, g of x. And what is this? Well, this is the expectation, if you wish, of g of x t starting from mu, okay, or mu ptg. So let me write what is mu pi tx. Mu pi tx, it's, well, you start from y with a certain probability mu of y, then you jump from y to x, and you are at gx. Let me change the order of the summation. This is what I was trying to show you here, but maybe it's easier to show directly by performing the summations. So let me change the order of summation and sum first over x to get that this is ddt of the sum, so as I said, y, mu y. And when you sum over x, what you get, it's ptg computed at y. Now let me take the derivative, and I know that the derivative of PTG it's equal to L PTG or PTLG. Okay. This is what we proved, that the derivative of the semigroup is given by L. So now let's take finally the derivative and let's write it as PTLG. So this is the sum over y, mu of y, PT L G of y. Now I go back in my, okay, so let's do it here. So I have a new function, which is LG, and I just want to go back to express this term as LG here. So I have to do the computation backward. So let me do it here. So we have mu y. And what is PTLG? It's a sum over x of PT y x LG of x. And now let's change again the order of summation. And let's sum over y. When I sum over y, what I get is mu pt. Yx Lg of x. And finally, let's divide that. So, sorry, here it's I sum over y. So when I sum over y, this is mu pt at x, Lg of x. Let me divide by pi x and multiply by pi x. And recall that mu pt divided by pi, it's ft. So this is the sum of ftx lgx pi x, which is the scalar product of ft with lg. Okay? So up to now, so I don't want to erase that, what we proved is that ddt of ftg, the scalar product, it's equal to ft lg. This is what we proved. Right? You agree with that? And this is what we need, because now let me use the definition of the adjoint. Okay. We have this identity. So if I take g of x to be equal to 1 if x is equal to x0 and 0 otherwise, what we get from that, it's that ddt of ft x0 pi x0, it's equal to L star applied to ft and computed at x0 pi of x0. Okay? And this is exactly what I wanted to prove. Fine, so ft is differentiable, and we have this identity. Okay. Fine. So this is second lemma. And now I can go back to my proof and recall that what we are trying to do is to take the time derivative of the relative entropy. And by writing Ft as the Radon-Nikodym derivative, what we have to do is to compute this derivative. Okay? So let's compute this derivative. Let's use this equation. So first I take the derivative of Ft, log Ft d pi, and then plus I take the derivative of the second term, so this is Ft. When I take the derivative, I get 1 over Ft, L star of Ft d pi. Okay, so I claim that the second term is 0. Why this is 0? Because Ft cancels with 1 over Ft, and what remains can be written as the scalar product of 1 with respect to L Ft pi. So now let's use the definition of L star. So this is L applied to 1 Ft pi, and L applied to 1, it's equal to 0. Okay, so if you remember that L applied to 1, it's that you sum the line of the generator, and when you sum the line of the generator, you get 0, because this is the definition of a generator, right? You have all terms of diagonal are positive, and the term at the diagonal, it's equal to the sum with the minus sign of the other terms. So this is equal to 0. So the second term vanishes, and what we need to care about is the first. And the first, I will use the same argument that I'll write this as f log Ft. Okay? And what I claim is that this is bounded by 2 square root of Ft L square root of Ft. So let's prove this inequality. So we have here L, right? So this is what's, if I write down what this formula is, this is a sum over all x in E of pi x. I'm integrating with respect to pi x, fx, ftx, and then the generator. When the generator is applied, it gives me a sum over y of rxy, and then log of fty minus log ftx. Okay? And so I can write this as a sum over x and y of px rxy. So this is a positive term, because the rates are positive and pi is positive, of ftx. And here, let me write this difference as log of fty divided by ftx. Okay, and what I want to show is that this expression, it's bounded by 2 times square root of ftx. So if I compute the same expression, I will have ftx and the difference between square root of ft. So I want to prove that this inequality holds for all x and y, for all ftx, fty. Mind that ft is strictly positive. Right? Ft is the Radon-Nikodym derivative, so it's a strictly positive expression. So what I need to prove, let me call ftx a, fty b. So what I need to prove is that a times log b divided by a, it's bounded by 2 times square root of a, square root of b minus square root of a, for all a and b positive. Okay, if I can prove this inequality, then this is true. So I can bound this expression by this expression, and then I will get, we will see what I claimed. So in order to prove that, let's divide by square root by a on both sides. So a and b are strictly positive, so I can divide by a. By dividing by a, this inequality, it's equivalent to, well, 1 square root will cancel. And this will become that. So this is what I need to prove. Okay? And so let me call t b over a, which is positive. So what I need to prove, it's log t. It's bounded by 2 times square root of t minus 1. So this is the inequality I need. Okay, I think I can erase the statement of the lemma you recall. So this is what I need to prove. I see that at t equal to 1, this is satisfied because both sides are equal to 0. Now let's take the derivative. So the derivative of log t, it's 1 over t. And the derivative of this expression, it's 1 over square root of t. Okay? So there are 2 cases which we need to consider. Let's assume first that t is larger than 1. If t is larger than 1, then this expression is bounded. 1 over t is smaller than square root of t. And so you have 2 functions which are equal at 1, but the derivative of the first one, it's less than the derivative of the second one. Therefore, the first one is bounded by the second, for all t larger than 1. Okay? At t equal to 1, they coincide, but the derivative of the first is bounded by the derivative of the second, and therefore, the first is bounded by the second. Now, let's consider the case in which t is less than 1. Then, well, this inequality gets the other side. And now the same argument, well, you have 2 functions. They are equal at 1, but the derivative of the first, it's larger than the derivative of the second. And therefore, the first, it's smaller than the second, because its derivative, it's larger. Okay? So the fact that the derivatives satisfy these inequalities shows that, indeed, log t is bounded by 2 times square root of t minus 1. Okay? So we proved this inequality. So we proved, so let me replace this expression by this expression. So this is bounded by 2 times the sum over x by x square root of ftx times the sum in y of Rxy square root ft(y) minus square root of ftx. Okay? And this is L applied to the square root of f at time t computed at x. And therefore, this is equal to 2 times the sum of x. Okay, so let me write this as square root of f t L square root of ft. Fine. So we proved that the derivative of the entropy, it's bounded by this expression. And let me call this. So let me summarize what we just did. We proved that this is bounded by 2 times the Dirichlet form minus of the square root of ft. So here I just introduced the Dirichlet form. So the Dirichlet form of a function h will be equal to minus h LH. And so this is what we proved. Okay, let me introduce the Dirichlet form as minus h L of h. And with this notation, mind that there is no minus sign, so I multiply a minus minus to get that this is true. Okay, so this is called the Dirichlet form. And what we proved that the derivative of the entropy, it's bounded by minus 2 times the Dirichlet form of square root of f. So what I claim now is that the Dirichlet form of h, it's always bounded. And it's equal to 0 if and only if h is constant. So since dH is positive, this means that indeed the entropy decreases in time. But more than that, because this means, so let me write here, so let's take this equation, let's integrate it in time, and to get that the entropy of Ft minus the entropy of F0, so this is the integration on the left-hand side, that this is bounded by minus 2, the integral from 0 to t of d square root of Fs ds. Okay, and well, mind that this is positive, so I get from this inequality that the entropy of Ft plus 2 times the time integral of the Dirichlet form of square root of Fs ds, that this is bounded by the entropy at time 0, which is mu with respect to pi. Okay, and this is what this inequality tells us. Well, that if you can estimate the entropy of the initial state with respect to the stationary state, then you have a bound of the relative entropy of the state at time t with respect to the stationary state, but also a bound on the Dirichlet form of square root of f. And these two informations will be very important. And this is for free. I mean, this is general, absolutely general. Right? For any Markov chain, you have these bounds. So let me show that the Dirichlet form is positive. So let's prove this claim in order to conclude this argument. So the Dirichlet form of H, right, by definition, it's minus H LH. And I want to write this as minus 1/2 H LH. And the second half, I will write it exactly in the same way, but then I use the definition of the adjoint. Okay? I didn't do anything. This is just, and this is minus L plus L star divided by 2 of H. And this is what I will call the symmetric part of the generator. So Ls will be equal to L plus L star divided by 2. Right? So now you have to remember the formula we had for the rate jumps of L star. So remember that we have the following formula: pi x r star xy. It's equal to pi y r yx. Okay? So this is the formula we derived for the jump rates of the adjoint process. So what is Ls applied to a function f computed at x? Well, by definition, it's 1/2 of L applied to f. And this, okay, so let me write it, plus 1/2 of L star f applied to x. And now by definition of L, this is the sum over all y, rxy, fy minus fx, and plus the same thing but with L star. So here we have the rates for L star. Now you see that if I represent by Rs, so let me represent by Rsxy what appeared here. So this is 1/2 of Rxy plus R star xy. So I can rewrite this as this is the sum of Rs xy fy minus fx. Right? And so you see that this operator Ls is also a generator, because all these rates are positive. Because these rates are the sum of two positive rates, therefore this is positive, and therefore this is a generator. So Ls, it's also a generator. but the rates at which this process jumps are given by Rs, which is given by this expression. Okay, so this is what we call the symmetric part of the generator, the symmetric version of the process. Mind that in the case in which pi satisfies the detailed balance condition, so which means that R star is equal to R, then from this formula, Rs coincides with R. So in the case in which the process is reversible, which means that the measure pi satisfies the detailed balance conditions, then Rs is simply equal to R. But in the case in which pi does not satisfy, I introduced R star, the adjoint, and after R star, I introduce the symmetric. And what I claim is that the symmetric satisfies the detailed balance condition. So let's check that. Let's check that pi x R s x y it's equal to pi y R s y x. Well, this comes from the definition because this is the left-hand side. It's equal to 1/2 of pi x R xy plus pi x R star xy. Okay, but this is equal to 1/2. Now you have to recall these identities. So let me use both identities. So pi x R xy, so you have to replace the role of y and x in this identity. This is pi y R star yx plus the same thing here. This is pi y R yx. And this is exactly, so now you see that this is pi y R star yx plus R yx divided by 2, and this is Rs. So this is pi y Rs yx. Okay? So if pi does not satisfy the detailed balance condition for your generator, but it satisfies now for the symmetric part of the generator. So the symmetric version of the generator gives you a reversible process. So a process in which if you change the orientation of time, you get the same evolution. And what we have here is that we observe that dh is equal to minus the symmetric version of h. And with this identity, with the detailed balance condition, we will be able to show that the Dirichlet form is positive. Because the Dirichlet form of h, it's minus h, the symmetric part of h. And now, let me write this as minus 1/2. The summation, and this is pi x hx, then the sum of y Rs xy hy minus hx. So I divide that by 2 because I have here another term, and in this, which I write the same, x pi x Rs xy hx hy minus hx. So I just wrote that this expression is equal to that expression, which is written as minus 1/2 minus 1/2. Didn't do nothing, but now let me use the fact that Rs satisfies the detailed balance condition to write this as Rs yx. So this is the detailed balance condition. And now let me, I have a sum over x and y, right? X and y. So now let me change x to y and y to x in this term. So this still have a sum over xy, but here I have pi x r s xy, hy, hx minus hy. Okay, so the second term became this expression. And now let me compare the first with the second. I still have minus 1/2. So I want to put together the first and the second. So I have pi x r x y. This is fine. So 1/2 sum over x and y, pi x r s xy. And then here I have hy minus hx, which appears here but with the wrong sign. So let me put here plus and here minus. So that becomes hy minus hx. Now they are equal. And what remains, it's hy minus hx. So this becomes square. So this is the formula for the Dirichlet form. Okay. So what we proved is that dh, it's equal to 1/2 the sum over all x, y, pi x, r xy, hy minus hx squared. And this is, of course, positive. So we just proved that the Dirichlet form is positive. Okay. This was my, and here is Rs. It's positive, and now the second claim is that assume that it's 0. Well, since all terms are positive, if this sum is 0, it means all terms are 0, which means that hy is equal to hx whenever rs xy is positive. Okay, but since the process is irreducible, I can find a path from x to y. Okay, and I will conclude that each, so let's call this path x0, x1, xn, where xn is equal to y. From this, if this is 0, this means that hx1 is equal to hx0, because this jump rate is positive. Then hx1 has to be equal to hx2, and so on. And I will conclude that hx is equal to hy. Is that clear? So this is my second statement, which means that if the Dirichlet form is 0, means that the function is constant. But here we are using irreducibility. So if the process is not irreducible, like in the exclusion process is irreducible only if you fix the total number of particles. Okay, so we proved that the Dirichlet form is positive, and this concludes the proof of the lemma. Right? So what was the claim? The claim. So what we proved, let me remind you, is that, let me call ft the random-Nikodym derivative of mu pt with respect to a stationary state pi. So let me call h of t the relative entropy of mu pt with respect to pi. And we obtained the inequality that ht plus the time integral from 0 to t of the Dirichlet form of the square root of fs ds, and maybe with a 2 here, which that this is bounded by the entropy at time 0. Okay. So, and these are the bounds I will need in order to prove these, to close the martingale in terms of the empirical measure. But as I said, this is a general property of Markov process, Markov chains. And we proved it here in finite state space, but you can extend all these estimates to much more general process. So questions? So what I want to do is to conclude by computing the Dirichlet form in the case of the exclusion process. Okay, we have seen that the exclusion process so the generator of the exclusion process, the one I introduced yesterday, can be written as the sum over all x of, here I wrote 1 plus a times eta x minus e plus eta x plus 2e of f sigma x x plus e eta minus f of eta. Okay. So this is, so let me write this as a function c of the translation of my configuration eta. So remember, tau x is just a translation of a configuration eta. So c of eta is here a function which is 1 plus a eta minus e plus eta 2e. So if I compute c translated by x, I will get here x minus e and here x plus 2e. And this is tau x of c of eta, by definition of tau xc. Okay, so let me write this generated in this simple form. And what we have seen is that L is reversible. Reversible with respect to the Bernoulli measures nu alpha. So pi will here be the product measure with density alpha. And I want to compute the Dirichlet form. And here is the formula for the Dirichlet form. Since the process is reversible, this means that the symmetric piece is equal to R. Okay. So let me compute, in the case of the exclusion, the Dirichlet form of function h. Okay. There is a problem of notation here because x represents a point. So now our points or elements are etas, are represented by eta. So here I have a sum over all eta and xi. So this is equal to, I'm just writing what is over there, but replacing x and y by eta and xi because we are representing our configurations by these letters. Okay. Then I have nu alpha of eta r eta xi, and then h xi minus h of eta square. Okay, so this is the Dirichlet form that we just computed. And now I have to remember that this is 0 unless xi is equal to sigma x, x plus e of eta. And if psi is equal to sigma x, x plus eta for some eta, then this rate is equal, the rate at which I jump from eta to sigma x, x plus e of eta, this is sigma, what I call there, tau x, c of eta. Right? Do you agree? Okay, these rates are always 0 unless sigma psi, it's a configuration which is in the neighborhood of eta. And the configuration in the neighborhood are those which can be written over there as this. And in that case, if sig psi is equal to this configuration, then the rate is given by that. So actually, this sum over psi is a sum over x this rate now it's given by that expression, tau x c of eta, and psi is this configuration, sigma x, x plus e of eta minus h of eta square. Okay? And so we have a formula which is 1 over 2 sum over x, and here an integral of tau x c of eta times h sigma x, x plus e of eta minus h of eta. This is square, and this is integrated with respect to nu alpha. Okay, so this is the formula for the Dirichlet form in the case of the exclusion. Right? Now, suppose that I have a function h whose Dirichlet form is equal to 0. If the Dirichlet form is equal to 0, it means that all these terms are equal to 0. So this means that h of sigma x, x plus e of eta, it's equal to h of eta for all x, or all x. So what does that mean? Well, I claim that this means that h of eta is actually a function of the sum of the particles. Okay, because if you take two configurations which has the same number of particles, then from this identity, so let's assume that I have psi and eta have the same number of particles. Okay? They have 3 particles. Now I know that h satisfies this identity. So this means that h of this configuration, it's equal to the one in which I move this particle for there, which is equal to there. And I can move this particle up to this and get that h of psi, it's equal to h of this configuration. And now I can move this particle up here and get that h of psi, it's equal to h of this configuration, which is h of eta. Which means that if I take any two configuration with the same number of particles, then h is equal at these two configurations. And this means that h is a function of the total number of particles. So if you fix the total, if you fix this hyperplane, then h is constant over this hyperplane. But the value at each hyperplane can be different. Right? Because here we have only informations about configurations with the same number of particles. Okay? So while in the irreducible case, if the Dirichlet form is 0, we get that h is constant. Here, what we get is that h is constant on each irreducible hyperplane, right? If you take a set of all configurations with k particles, this set is irreducible. And what we are getting is that if the Dirichlet form of function h is equal to 0, means that this function is constant along each what I will call ergodic or irreducible set. Okay? Fine. So we are now in a position that we can go back to our problem and try to prove that that martingale can be expressed as a function of the empirical measure. But that I will leave it to tomorrow. Okay, so we stop here and we continue tomorrow with what I was doing yesterday.